hello again. And this work is done in collaboration with Mary Network and the University of Massachusetts, Amherst. So censorship and all kinds of restrictions have been on the rise around the world, and more users are turning to circumvention in response. And this is a typical circumvention scenario where you have users behind the firewall encapsulate their traffic within a tunnel that goes to a proxy server outside the censored region, which then forwards the traffic to the final destination. And the tunnel encrypts the traffic within so that even if the user is trying to access a blocked website, the censor will not see this and will not be triggered. So this is a scenario we consider in our study. The most important point here is that the tunnel itself must be obfuscated, because censors are always motivated to detect and block such circumvention efforts. And over the years, the circumvention community has come up with different obfuscation techniques like shadow source Trojan that provides the necessary cover for this tunnel. This leads to an ongoing conflict lasting for over a decade now that some might call it a cat and mouse game. On one side, you have circumvention system implementing different obfuscation covers. And on the other, censors constantly find new ways to detect them. For example, censors were able to fingerprint shadow source by sending special probes and observing the specific reaction from a shadow source server. Or consider Snowflake, which David just mentioned. Snowflake was detected based on how it implemented DTLS as its cover, which differed only slightly from mainstream browsers, but created unique and subtle fingerprints. So these are just two examples out of many documented fingerprinting attacks that all exploited the specific the design or implementation flaws specific to each of these cover protocols. I want to emphasize on how these attacks are protocol specific. Indeed, almost all of them rely on very specialized fingerprints. A fingerprint for shadow source, for example, wouldn't work for Snowflake. And the conventional wisdom here is that each individual cover protocol would require its own unique set of features and separate analysis process from censors to develop these specialized fingerprints. So this led to this principle or strategy called letting 1,000 flowers bloom. The idea is that since each cover protocol, each specialized fingerprint takes a long time and manual efforts to develop, the more protocols we can create, the less likely a censor has the resources to target all of them at the same time. And this is the thinking that motivated our study. We're not saying that creating new protocols to stay ahead of the censor is not a reasonable approach. But we do want to question, do censors really need to examine and fingerprint each cover protocol separately? We have to recognize that censors don't actually care whether you are using shadow source or something or some other protocol. What they care about is simply, is this flow carrying circumvention traffic or not? Let's look at what happens when you try to circumvent the firewalls. Imagine you are browsing the web using a proxy. You first create a tunnel to your proxy server. And inside this tunnel, your browser initiates an end-to-end HTTPS connection to the website you want to visit. This inner end-to-end HTTPS, including the TLS handshake at the beginning of it, client hello, server hello, and so on, happens entirely within the already encrypted proxy tunnel. The cover of the tunnel can be anything, which depends on the specific cover protocol you are using. If you're using a TLS-based proxy like Trojan, the tunnel itself can also be TLS. And in this case, we got two layers of TLS. The red one, the outer tunnel TLS that is visible to the censor, and the blue, the inner end-to-end TLS that is encapsulated within the payload of the outer TLS. I want you to focus on this inner encapsulated TLS, especially the handshake part of it. We call this inner handshake encapsulated TLS handshake. And what we demonstrate in this study is that this encapsulated handshake can be actually a strong fingerprint that actually provides censors a protocol-agnostic way to detect circumvention traffic. So why is this fingerprint a good indicator of circumvention? The key insight here is that all forms of proxying and tunneling, no matter what specific cover protocols they use rely on what we call nested protocol stacks, where one protocol stack is encapsulated entirely within the payload of another. This is exactly the behavior that creates the pattern we see in encapsulated TLS handshake. We chose to focus on encapsulated TLS instead of other protocols because TLS is everywhere. Circumvention users cannot avoid this fingerprint simply by not using any TLS. And also TLS is meant for end-to-end security. So when you see a TLS encapsulated within an already encrypted stream, like another TLS, that's unusual and suggests the outer encryption is not going all the way to the final destination, but instead being removed earlier at the forwarding proxy server. Let me emphasize this again. So we are not detecting shadow salts or any specific circumvention protocol here. What we are detecting is tunnels, and the encapsulated TLS handshakes is a fingerprint for the presence of the tunnels. So how does this fingerprint look like on the wire? The definition of encapsulated TLS handshake means that they are not directly visible. But TLS handshakes, encapsulated or not, are very structured and have very distinguishing patterns over size and direction of the packets. And each part of the handshake, client hello, server hello, key exchange, change cipher, logically depends on the one before it, so they always show up in the same order. This figure here shows a TLS over TLS scenario, which is what sensor sees if you do web browsing using a TLS-based proxy. You can clearly see the same pattern repeating twice in a row, and the first is the outer tunnel TLS handshake, and the second is the inner encapsulated handshake by your browser. These patterns in size, direction, order remain visible even after the tunnel encryption, which allow us to identify these encapsulated handshakes without having to break the encryption of the tunnel, of the cover. We implemented this fingerprint to show it can work. Very briefly, we approach this as a binary classification problem to determine the presence or absence of encapsulated TLS handshakes from a traffic flow. We use trigrams and traffic bursts as features from sequence of packet sizes, and we use very basic statistical tests to compare that to what we expect. A key point here is that we don't actually need to learn what encapsulated TLS handshake look like from genuine circumvention traffic, which can be hard to source. Instead, we can look at normal TLS traffic and adapt what we learn to work on encrypted flows. So let's talk about how effective this fingerprint is in practice. For evaluation, we play the role of a sensor and actually deploy the fingerprint inside a real ISP for months. We tested this on traffic from real users that are served by the ISP and also circumvention traffic that we generated ourselves as a customer of the same ISP. We tested 23 different obfuscated proxy configurations, including the most popular ones like shadow salts, UMass, Trojan, and others. First of all, I want to point out that the fingerprint's effectiveness is largely independent of the cover protocol used, which is expected because we are not looking for covers, but for the science of tunneling itself. So every obfuscated proxy protocol we tested by default was vulnerable to the fingerprint. To provide some context on the practicality, this shaded area in the graph shows the false positive rates of the real-world attacks we've seen before. The 4 major circumvention protocols all had the detection rates over 70%, even under a conservative false positive threshold. And we think this is concerning, considering these protocols were designed precisely for circumvention, and obfuscation is their top priority. We also tried adding more layers of encapsulation, like covering circumvention traffic within shadow salts, and that within a WebSocket, and then within another layer of TLS. The detection rates remain significant. And even with very aggressive random padding, where all packets are padded to the same size range, we could still use directions as a feature. It's less informative, of course, but still gives a decent balance of detection and precision. So in fact, we found connection multiplexing actually shows more promise as a defense than padding alone. Multiplexing allows different data streams to share a single connection, which interleaves packets from different streams and potentially disrupt the pattern over the fingerprinting pattern. while it does not eliminate the fingerprint entirely, it does significantly reduces the detection rates. So as we work on a more principled solution to this vulnerability, multiplexing could be a potential defense for the short term. So let me end with a recent incident in Russia. So far, we've been discussing this potential attack vector as largely preemptive, trying to anticipate the censor's next move and establish proactive defense. But 3 months ago, Russian censors started testing a new method for blocking circumvention traffic. And their new approach was very similar to what I just described here. They were not going after cover protocols anymore, but trying to detect TLS handshakes that are encapsulated within. So to be clear, their implementation was very different from ours, but the concept was exactly the same. While the incident appeared to be only a test run and the blocking was temporary, we do think it signals where the censorship is heading next. So unfortunately, it's no longer about forward thinking or staying ahead. It's about addressing a real immediate issue to the efficacy of many circumvention efforts. With that, thank you again, and I can answer a few questions.